Have you ever really thought about that camera in your pocket? I mean, how does this little slab of glass and metal actually freeze a moment in time? Well, we're going to pull back the curtain and look at the incredible physics and, the straight up computation that goes into every single photo you take. Just let that sink in for a second. The light that actually created the image you're looking at, it's gone. It vanished the very instant the shutter clicked. So in a way, every photograph is kind of a ghost. It's a permanent record of light that isn't there anymore. So that's the big question, right? How on earth does a machine capture something as fleeting as light and then turn it into a permanent image we can hold or, post online? It's a journey that takes us from pure physics all the way to raw digital data. Okay, so the whole journey starts the moment light enters the camera. And the very first thing that this vanished light runs into is the lens. And, its job might not be what you think it is. Right, let's clear up a huge misconception. We tend to think of camera lenses as like fancy magnifying glasses, but their main job is really to be a traffic cop for light rays. They take all these scattered rays bouncing off a single point on an object, and they bend them, they converge them onto one single sharp point inside the camera. And that's all focusing really is. You're just adjusting the lens so that perfect point of convergence lands exactly on the sensor. So once all that light is focused, it snacks right into the heart of the digital camera, the sensor. You can basically picture it as a giant grid made of millions of tiny little buckets. These are called photosites, and each one is just waiting to catch the light that will eventually become a single pixel in your photo. Now, this all works because of this amazing little bit of physics called the photoelectric effect. When a particle of light, that's a photon, hits a photosite, its energy literally knocks electrons loose from the silicon. And here's the crucial part. A brighter light means more photons are hitting it, which means more electrons get knocked loose. The camera is, quite simply, counting those freed electrons. So, let's walk through that again. Light comes through the lens. A photon hits one of those little photosites, knocking some electrons free. The sensor then measures exactly how many electrons were freed, and that number, that electron count, gets converted into a brightness value. It's really that simple. More electrons equals a brighter pixel. It's a direct conversion of light energy into a digital number. Now, to control how much light gets counted, photographers have three main tools. The aperture is just how big the opening in the lens is. The shutter speed is how long the sensor is exposed to light. But ISO is a little different. It doesn't actually make the sensor more sensitive. It just amplifies the electrical signal after the light has already been captured. And that's why, when you crank up the ISO for a night shot, it starts to look all grainy. The camera is amplifying a really weak signal, and it's amplifying all the random electrical noise right along with it. Okay, so that's brightness. We get that. But what about color? This is where things get really clever, because it turns out digital cameras are hiding a pretty big secret. That's right. The sensor itself is completely colorblind. All those little photosites we just talked about, they can only do one thing: count how many photons hit them. They measure the intensity of light, not the color. So to the sensor, the world is nothing but shades of gray. Which, leads to a pretty obvious question, right? If the camera's hardware is colorblind, then how in the world do we end up with these incredibly vibrant, colorful photos on our screens? Well, the solution is just an absolutely ingenious piece of engineering. The answer is this microscopic checkerboard called a Bayer filter that sits right on top of the sensor. It's a grid of tiny red, green, and blue filters with one little colored filter over each individual photosite. So now a photosite under a red filter can only measure the brightness of red light, and the same goes for the ones under green and blue filters. The camera's brain, the processor, then looks at a little group of these single-color measurements and makes a really smart, educated guess, combining their brightness data to reconstruct what the full color must have been for that spot. This amazing process is called demosaic, and it's a huge reason why a digital photo is a reconstruction of reality, not just a direct copy. And that whole idea of reconstruction, that brings us to the final and I'd say most modern step in how a photograph gets made. Because today, especially with the cameras in our phones, the work is far from over once the light's been captured. Seriously, the incredible quality you get from your phone's camera, it's not just about the lens or the sensor anymore. It's almost entirely thanks to something called computational photography. Your phone isn't just taking one picture, it's running incredibly complex software to intelligently build a better one from the raw data it collected. And you can really see the difference this makes. On the left is kind of what the raw data from the sensor looks like. It's noisy, maybe a little soft, and it struggles to capture both the really bright parts of a scene and the really dark shadows. But on the right, that's the final image after the phone's processor has worked its magic. It's gotten rid of the noise, it's computationally sharpened details, and it's blended multiple exposures together to create a high dynamic range or HDR image, where you can see everything clearly. In fact, a lot of the time when you press that shutter button, your phone isn't taking just one picture. It's secretly capturing a super fast burst of photos at different settings. Then it intelligently merges them all together. It might take one frame just for the bright sky, another for the dark shadows, and maybe a third just to get the sharpest details. And then it combines them all together to create one final, calculated result that looks way better than any single photo ever could. So what this all means is that a camera doesn't give us a perfect window into what's real. It samples reality. It takes a measurement of light at millions of different points for a tiny fraction of a second, and then it uses a whole lot of math to reconstruct a plausible image from that very limited set of data. And that really leaves us with a final thought to chew on. If every single photo you've ever seen is a heavily processed, calculated interpretation of light that's already gone, what are we truly looking at? It's not really a frozen moment in time. It's a record of measured light that's been shaped by both physics and software. And you know what? That kind of makes every single image you see just a little more amazing.